So we're dealing with unit 1, okay, for mathematics for economics. We're on differentiation. Just a small recap of what we did last time. First, we talked about the derivative, right? Just talking about the rate of change over something. Okay, that's what the derivative is telling you, the rate of change of something. Okay, and we needed to remember the power rule, which is a basic concept of differentiation. All right, so here with this example here, y equals x squared. All right, we want to find the rate of change basically. All right, so we need to derive this. So as I said, when deriving, you multiply the exponent or the power with the coefficient. 2 times 1, that is 2. You put an x here. Then after you multiplied the power with the number in front of the letter, which is called the coefficient, you always subtract a 1 from the exponent. 2 minus 1, that is 1. That's how we get 2x. Do we remember this, colleagues? The power rule, because it's the heart of differentiation. So do we remember this? Any questions on that before we move to the next part? Okay. So as you can see, for example, if x equals 3, you just put the 3 into this function. 2 times 3, you get 6. So that is the rate of change. Okay, if x increases by 3, your function will increase by 6 units. Now, how we apply this differentiation in economics? All right, if you remember, you've got what we call marginal cost, marginal revenue. All right, what's the definition of marginal cost, colleagues? Because I'm taking it all of you are economists here, so this must be your second language. What is the marginal cost? Excuse me. Madam Prudence, Mr. Chipipa, Madam Cecilia. Okay, marginal cost is the additional cost you incur. Additional cost you incur when you produce an extra unit. Okay. So marginal cost, you can think of it as the rate of change of the total cost, basic. Okay. So for example, if your total cost function is this one, TC equals 100 plus 2q squared. Alright, and then you have to find the marginal cost.
Hello, hi.
Hello.
It's the additional of
Yes. You are breaking, madam. No, but I believe you said the additional cost you incur when you produce an extra unit. So you must remember the point of profit maximization, where marginal cost equals marginal revenue. Okay, you might be given questions where you are given a cost function, a revenue function, then they'll ask you how much should a company produce to maximize profit. So you need to remember how to get your marginal cost or your marginal revenue. Okay, so if you're given a total cost function like this and you want to get the marginal cost, it means you need to derive this total cost function. All right, so when deriving, remember any number that doesn't have a letter disappears. And the good thing about it is you don't need to show how it disappears, it just disappears. So this 100 goes. Then this 2q squared, you multiply the exponent 2 with the coefficient number in front of the letter. 2 times 2, you get 4. Then you subtract a 1 from the exponent. 2 minus 1, you get 1. Okay, so our marginal cost is 4q. Okay, so as we said, it's the additional cost whenever you produce an extra unit. So if q equals 1, because an extra unit is 1 unit, right? So if q equals 1, 4 times 1, you get 4. You just get 4. Okay. It can be 4 kwacha, $4, 4 pounds. So when you say your marginal cost is 4, it means when you produce an extra unit, you incur a cost of 4 kwacha. You produce another 1 unit, you incur a cost of 4 kwacha. If you produce 5 units, you incur a cost of 20 kwacha. Okay. Yes. Any questions before we go to the next section, which we also looked at last time, was for partial differentiation? Any questions? Okay, partial derivatives. This is when your function has got more than one variable. Okay, if you saw the functions earlier here, you've just got one variable, like in this one here, y equals x squared. The only variable is x. In this cost function, the only variable is q. Okay, so you're just dealing with one variable. Now if you're dealing with 2 or more variables, this is where partial differentiation comes in. All right, basically the whole essence is you're deriving one variable while holding the other variable constant. Okay, oops, let me just get some bundles. Sorry about that, was kicked out. Yes, as I was saying, partial derivatives is where your function has got more than one variable or more than one letter. Okay, so you're deriving one variable while holding the other variable constant. Okay, so as we can see here, you've got this function here, z. It's good. We've got 2 variables, x and y. Okay, so this symbol here, this symbol like this one here, it tells us it's partial differentiation. You're deriving only one variable while holding the other variables constant. Okay, so if we look at this function here and want to derive it, we need to derive first with respect to x and need to derive with respect to y. Okay, so z equals x squared plus 3x, x squared plus 3xy plus y squared. So if we derive this function with respect to x, you're going to say like this: you're deriving the z function with respect to x, meaning the only variable you're focusing is on x. Okay, if a term doesn't have an x, it disappears. So here, like this y squared, won't consider it because it doesn't got an x. Okay? So we're only going to derive this x squared and this 3xy. So when we derive x squared, we get 2x plus, we derive this 3xy. Remember, this x is to the power 1. So you multiply 1 times 3, 3. Then 1 times, we subtract a 1 from the exponent. We subtract a 1 from the exponent. 1 minus 1, that is 0. So this x has remained x to the power 0. So when we derive, it becomes just 3y. And that is our solution when deriving with respect to x. Any questions? Can we derive this function with respect to y now? Can we derive this function with respect to y?
That's 3x plus 2y.
That's correct. Any questions? Okay. Yes. So in economics, for example, we have a profit function here, which is dependent on two products, x and y. Alright, so what our partial derivatives are going to tell us, if we derive this function with respect to x, okay, it's just telling us how our profit changes if the firm increases the product x while keeping y constant. Okay, when I repeat, when you get the partial derivative of this profit function here with respect to x, it's just telling you how your profit changes if you increase product x while holding product y constant. Okay, so here, if we derive this function with respect to x, this 5x squared becomes 10x. This 3xy becomes 3y, 10x plus 3y. Okay, so this is going to tell us how profit changes if product increase or decrease product x while y is constant. And if we get the partial derivative with respect to y, okay, it's just telling us how the profit changes if we increase product y while keeping x constant. So if we derive this function with respect to y, it becomes this we don't derive it, we derive this, that becomes 3x plus and this 2y squared becomes 4y. Okay, so this partial derivative, how the profit changes if you increase product y while keeping x constant. So any questions before we move now to total differentials? So total differentials is just basically talk about the total change that will happen when you incorporate the rate of change of x and incorporate the rate of change of y. Okay, the total change that will occur to the function. Okay, it's basically just a continuation of this. Okay, so for example, if they had to ask us get the total differential for this same function here, this let's see here. Pi xy squared plus 3xy plus 2y squared. Okay, so as you can see, want to get the total differential, it means you're just first going to partially derive x and you're also going to partially derive y. Okay, so when we derived x, when we partially derived x, okay, we got 10x plus 3y. So you're just going to put here 10x plus 3y. Okay, then in brackets, then you add outside the brackets, you just put dx plus the partial derivative of y, which was 3x plus 4y. Okay, so this is just telling us the total change in the profit function when we incorporate the change in x and the change in y. Okay, so the total differentials is just like a continuation of the partial differentiation. After you have partially derived, then you combine them together at the end like this. Any questions before I give you one to try here? We derived, remember, we derived this function with respect to x. Remember, we got, we got 10x plus 3y, which is here, 10x plus 3y. Then we derived this function with respect to y and got 3x plus 4y. So, yeah, so basically these partial derivatives we calculated earlier on, we're just putting them together like this.
Okay.
Yes, just putting them together. Okay, so here's one to try, because as I said, mathematics, very practical. Get the total differential for this function x cubed y squared. So just remember, get the partial derivative with respect to x, get the partial derivative with respect to y, and then combine them at the end. So let's see what we'll get.
So for this question, sir, we're not getting the partial derivatives. We'll just use these ones, the ones that you worked out. So only getting the total derivative.
No, you're getting the partial derivatives, then you're combining them at the end. That's what the total differential is. How the total function changes with when you combine the changes with respect to one variable and the change with respect to another variable. Just think of it as just the total change, okay, colleagues? The partial derivative was the partial change. Total derivative is the total change.
Hello, sir. Okay, not so sure. I'm still trying to grasp it. So that's I'm using from what the analysis that you're saying at, you just add the two. So that's 10x.
Madam, we're doing this one here. Which one are you deriving?
Oh, okay. I thought you were telling us to find the total derivative of the one above.
No, we found it. For this one, we found the total derivative of this one here. It's already...
Okay, the network is breaking. Maybe I just missed that.
Okay. Has anyone else found the total derivative of this function here?
So we're finding the total derivative of is the 5x squared or the one you've just written.
U equals x cubed y squared. Okay, that's the partial derivative of thing x, right? And 3x to the power 2. 3x squared.
3x to the power 2. If we find the x, so then y to the power 2.
Yes, that's correct.
Then the other one, with respect to y, x to the power 3, then 2y.
2, we put the number first, so it's 2. So this 2 has come here, okay. You put the number first, so 2x cubed y. Okay. Because it won't look nice, you put like this x cubed, then 2y here, like this. Never leave an answer like this. Okay. Yes. So the total derivative is, you're now going to put, you're going to say 3x squared y squared, in brackets you put dx, plus 2x cubed y dy. Okay, this is our utility function. Whenever you see a u like this is just a utility function. Utility is just satisfaction. Should we try one more? Oh, any questions? Okay, any questions before we try one more? Are there any questions on this one?
Yes.
Okay.
We're getting 2x to 2x to the power 3y. Is it supposed to be 2x? Then just go back. Go back.
Read. Ask the question again.
I'm saying for the second one. We're driving with respect to y.
With respect to y, yes.
Yes. Is it supposed to be 2x? 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 Then 3 to the power 3, to the power y2.
That's, if you are deriving with respect to y, madam, you're only deriving this y squared here. So this 2 times the 1 in front of this 2, it is 2. Then you subtract a 1 from this 2. That's how we've just remained with a 2x cubed y there. That's with respect to y. You just focus on this y variable and its power. Is that okay, madam, or I need to re-explain it? Is that okay?
Okay, you re-explain it just for one last time.
Our function is u equals x cubed y squared. Okay, so first you want to derive this function with respect to x, meaning you're only focusing on the x variable. So if we derive this function with respect to x, the exponent for x, 3 times 1, that gives us 3. Subtract a 1 from this exponent, 3 minus 1, that is 2. So you get 3x squared. This y squared, you leave it you just leave it like that. Don't touch or mess with it. Are we clear with this one? Any questions on this one? If I go to now y?
Yes. I'm good.
So now we differentiate this u function with respect to y. So it means this time we're focusing on the power for y. So you're going to say 2 times 1, that gives you 2. The x cubed stays the same, it remains untouched. You subtract a 1 from this power. 2 minus 1, that is 1. So 2x cubed y. So the total derivative we just add these two. Like that.
Okay, so you know what I was trying to understand is where was we're driving this in respect to y, yeah?
Yes.
So I was just trying to understand why we're multiplying this power 2 times the variable in front of x instead of y.
You can also think of it as since think of these two as they are married, so there's just a 1 in front of both of them. Okay, I think that way to make life easy.
Oh, okay.
Think of them as together, then there's so now here try to get the total derivative of this one. What does happen here? Because you have to remember, sometimes they will separate them like this, sometimes they will be combined, so you need to know how to do it. So let's get the total. Again, the total derivative.
That's 3x squared dx
Let's do it in steps. Partial derivative with respect to x, 3x squared, right? Yes, this is how this utility function increases with respect to x when you hold y constant. Then the next one,
and then the partial derivative with respect to y, that's 2y.
Then the final answer.
So the total derivative with respect to x and y, that's equals to 3x squared dx.
Yeah.
Dx plus 3x squared.
Yes, 3x squared dx plus 2y dy.
Plus, yes.
Okay. Are we all okay with that?
Yes.
Okay. go to homogeneous functions, here's one. Get the total differential for this one. Just write the same question. Ux1, x2. X1 squared, x2 cubed, anyone found the answer?
Yes, I have.
Okay, what's the partial derivative for x1 when we derive the utility function with respect to x1?
So that's 2x1 plus 1
plus x2.
Hello?
Plus x2. This one. Let me show you how. Let me show you the answer. Yes, so this x1 squared, when we derive it, it becomes 2x1. And this one, this x2, we're not deriving, it's not part of this.
Yes.
Then here, this x1, x2, this x1 is to the power 1. 1 times 1, 1. You subtract a 1 from here, 1 minus 1, 0. So this so this x1 is like x1 to the power 0. So you just remain with an x2.
Okay. And that's why I forgot that we have the x2.
Then partial derivative with respect to with respect to x2.
That's 2x2. The one at the bottom.
What? Derive this one first. This x2 cubed.
Oh, cubed, not squared?
That's cubed.
Oh, okay. So that's 3x2, the 2 at the bottom, to the power 2, plus x1.
Plus x1, yes. Yes. Any questions? So our total derivative.
So our total derivative will be 2x1
plus
x2 dx1
yes,
and plus 3x2 to the power 2 plus x1 dx2.
Any questions? I see sometimes they like to bring these roots here, so I need you to know what to do when you see these roots here. Okay, if that asks, get the total differential for this one. How would we do this, colleagues? Remember, whenever you have these roots, to get rid of it, it's the same as saying it's to the power half. Okay, x y to the power half. Rules of indices. Okay, remember this rule of indices: a to the power m over n. Okay, whenever you've got a fractional index, the denominator comes before the root. So you say the square root of n, or the root of n. Then this power, this numerator, will come inside here. The power m. Okay. So here, it's like there's a 2 outside, and there are these ones inside here. X to the power 1, y to the power 1. Okay. So this converts to that. Are we clear on that point? Madam Prudence, Madam Cecilia, Mr. Chipipa.
So, the bottom answer, that's the final answer.
No. That's we haven't even get started. Because next, what you're supposed to do is then this power distribute it to each letter. So this becomes x to the power, x to the power half y to the power half. So I always advise, fractions make life a bit difficult, so use decimals. Okay, convert them into decimals if you want to make life easy. So x to the power 0.5 y to the power 0.5. Can we now try to get the total differential?
So, in respect to x, that of 0.5,
partial derivative with respect to x is 0.5.
X
To
to the power negative 0.5 y 0.5.
Then whenever you have a negative power, bring it to the
0.5 y to the power 0.5 over x to the power 0.5.
yes. Then with respect to y,
That's 0.5 x to the power 0.5 y to the power negative 0.5. X to the power 0.5 over y
why is it done that? Over y to the power 0.5.
Yes.
Colleagues, are we okay with this? Then you just add this x, this dx plus this dy. Yes. Any questions? Okay. Now, are we ready for degree of homogeneity? Homogeneous functions, I mean. Or we pause here. Okay. Because so tomorrow.
Kindly share the questions that we're looking at.
Okay, I'm going to share everything.
Thank you.
Yes, because